Good evening, I am Mr. Ish. Thank you for joining me. In this video, let's achieve some finality when it comes to midpoint and trapezoid rule comparisons. We have a function over here which is easily integrated by our polynomial substitution technique. Let us demonstrate the area of this and we can compare them to that when we are using approximation techniques such as the midpoint and the trapezoid rule. If you want to integrate this using the basic technique, you know you're going to do u is equal to 2 minus x, and then du is equal to minus dx, and dx is equal to minus du. But you also know you have a definite integral, therefore your intervals must change with regards to this. u1 will be 2 minus 0, which is 2. u2 will be 2 minus 2, which is a 0, and your definite integral will become this, because you have a minus sitting out here. You'll have a 2 and a 0. You'll have u to the 1 or 2 du. But you can use the properties of intervals and integrals and flip everything around with another minus, and you can achieve your original interval setup, and you still have the 1 or 2 here with regards to the power, and that's what you have. In the end, what you end up developing here is these cancel out. You have u to the 3 over 2 over 3 over 2, and you know, from 2 to 0. What we have to do here is actually bring out the calculator. We'll develop this in terms of a good answer, because 0 is meaningless. That's exactly what it boils down to. We have 2 exponent 1.5 times 2 divided by 3. We'll have 1.8856, and let's put this value here, 1.8856. That's the accurate area with regards to the number of decimal places I have. Now let's bring in the midpoint rule. We'll do it right over here, and then we'll do the trapezoid rule. We'll do n is equal to 3 with regards to that. 3 appears to be a good number. Alright, we have the function written over there, and we have the interval. We can set aside this interval width. We can do b minus a divided by n, which will be 2 minus 0 divided by 3, and you know it's 2 over 3. That right there is our interval. Now for the midpoint rule, let's do our intervals over here. We can do our sample points using the midpoints, and then you know we'll do the function here, f of xi, but here we'll do just 2 minus x, because that is our function. Our intervals are not hard. We're going by 2 over 3s. We can do here from 0 to 2 over 3, and then 2 over 3 to 4 over 3, and then 4 over 3 to 6 over 3, and everything falls into place. When you're doing the middle of 0 and 2 over 3, you know you're getting a 1 over 3. The middle of this is a 3 over 3. I'm just keeping everything here over 3. I'm not simplifying anything, just for consistency. And here we have a 5 over 3. What we need to do is bring out the calculator. We'll plug in these x-axis values and we'll put them in here. What I'll do is I'll plug in each of these x-axis values here, and I'll solve it out, and I'll put the result over here for you. So that right there are the results of placing each of these values here in place of x and solving it out. You know, now all you have to do is sum these up. When you add these up and you multiply them by this interval width, you'll easily get the area, and we'll plug in the area and we'll solve it out. I'm going to sum all of these, and then I'll multiply them once with that interval, and I'll put the value here for you. Again, we're adding these individual items, which are your f of xi, the lengths of each of the Riemann rectangles, multiplying it by the width of each rectangle. When I do this midpoint rule, the area determination, I get this value, and I'm putting it for you right over here. 1.9122298. You can see we're slightly higher in terms of this area right here, but that's fine. This area has been done. In the end, we can get the error rate or the error amount. For the trapezoidal rule, you know you still have the same intervals. You know how it's going to be. We have the delta x divided by 2, then we have the f of x0, and since there's n value here of 3, we should have 4 terms, n plus 1. That's how it plays out. We'll have 2 times f of x1 plus 2 times f of x2 plus the terminal value placed in, but with a coefficient of 1. There it is. That's the formula. We have all of these values. x0, first value, second value, third value, fourth value. Everything will fall into play. We have our delta x is a 2 over 3. Our width, 2 over 3 divided by 2 is a 2 over a 6, which is a 1 over 3. Delta x divided by 2, utilizing that, I'm getting a 1 over 3. Now basically what I'm doing is putting these values right here, 0, 2 over 3, 4 over 3, 6 over 3 into this function right here. I have to put them in. When I put 0 in here, I'm getting a root 2. What I will do is put each of these values 0, 2 over 3, 4 over 3, 6 over 3 into this, and I'll plug in the values over here multiplying by the appropriate coefficients, and I'll put them here for you. Okay, these are the values I get. When I put a 0 in here, 2 minus a 0, I get a root 2, and I've left that as is. When I put 2 over 3 in place of x, I solve it out, I multiply by coefficient 2, I get this 2.309401077. When I put 4 over 3 in there and I solve it out, do the root, and I multiply by 2, I get 1.632993162. And lastly, when I put 6 over 3, which is a 2, I'm doing a root of a 0, which is just a 0. What I will do now is I'll add all of these, I'll multiply by 1 over 3, and then I'll put this area value from the trapezoidal rule for you, and then we can do some comparison. The area value I'm getting is 1.78553. We can even put another digit. That's what I'm getting. Now look, here the midpoint rule is developing a value which is slightly higher than the true value. The trapezoidal rule is developing a value which is slightly less than the true value. We can get the error amount. The error amount will be the true value minus our approximated value, and we'll do that. My error amount using the midpoint rule is this, minus 0.0266298. Utilizing the trapezoidal rule, my error amount is 0.100064. Now in this instance, based on these error amounts, you can see clearly what the difference is between the two. We're here off by 0.1, but here we're off only by 0.02. Don't worry about the signs. The signs I determined from doing the error amount. I was doing the true value minus the approximated value. Because this was higher, when you minus the higher number from the smaller, I got a negative value, and from here I got a positive value. But look at the difference. Here we're at a 0.1, here we're at a 0.02, and you can divide them both, this 0.1 divided by that, and you'll get this value right here in terms of the error. We're 3.75 times higher. This trapezoidal rule area approximation is 3.75 times more inaccurate in terms of that. It is slightly more inaccurate. But in terms of the overall amount, this is still not way off. So we're still good in terms of our approximations. In the end, you can see here clearly that the midpoint rule always ends up being accurate. And you saw in the previous video, the example we laid out for you. Again, the midpoint rule was more accurate. But in both instances, sometimes it's difficult to predict which one will overestimate, which will underestimate. In this specific example here, the midpoint rule overestimated the area, but still the overestimation in terms of the discrepancy was less. The underestimation by the trapezoidal rule was quite a bit more in terms of the actual area. But that's it for this video. I hope you enjoyed it. Thank you for watching. Have a nice day.